So when you consider two functions, f and g, that are continuous in a certain interval and one is bigger than the other, you have the situation where there's going to be certain area enclosed that those functions. So as you can see here, we have an upper curve f given by the function y equals f of x, and a lower curve given by the functions y equals g of x. Now this area that is down here can be approximated if we use the notion of integration. So first, we're going to rely on the slice and sum strategy for finding area with Riemann sums. So we're essentially going to take a partition on the interval AB and create rectangles where we can approximate the area that is in the middle of these two functions. Of course, we have a certain width of each of the rectangles, and we're going to be given the height and the base of these rectangles with the different functions f and g. In this way, if we consider a particular rectangle, notice that we can consider the base to be delta x, and the area of the rectangle is going to be given by the difference of the heights times that delta x, since that's going to approximate that given rectangle that we have in here. Notice that if we add up all the regions that we have right here, we have a sum of all these rectangles, and that can be approximated by the integral. So in that form, we can approximate, or we can find the area of a region between two curves by checking first who's the function that is bigger than the other, and making the difference between the top function and the lower function in the integral of a to b. So the definition of this is for the area between two curves, suppose that you're going to have two functions, f and g continuous, and with f bigger than g. That's going to be on the interval AB, and the area of the region bounded by the graph of f, g, and the AB interval is going to be the integral of AB of f minus g. So let's see an example of this. We're going to find the area of the region bounded by the graph of f of x equals 5 minus x squared and g of x equals x squared minus 3. So if we graph those functions, notice that this is going to be a parabola, and this is as well going to be a parabola. They're going to intercept a certain point. So here we have the top function is going to be the function f, and the bottom function is g. And in this scenario, at some point, those functions are going to intercept. And to find the points where their functions intercept, we're going to make equal 5 minus x squared and x squared minus 3. So let's take a look at that intersection on the board. So we have 5 minus x squared equals to x squared minus 3. So I can put numbers on one side and x squared on the other side. So we get 2x squared equals 8. So x squared is equals 4. And so x is either going to be 2 or x is going to be minus 2. So once that we have this intersection, we have this point. We can plug in any of the two functions, and we're going to find that these are the points minus 2, 1, and 2, 1. And we get that the interval for the area is going to be from minus 2 to 2. So the area between the two in case function is going to be the integral from minus 2 to 2 of f of x minus g of x. And we express that doing the functions, and the result of this is going to give us our answer for the area. We're going to skip the computing of this, since this is integration that we know how to do at this point. And let's move on to another example. So in example 2, we're going to find the area of the region bounded by the graph of f of x equals minus x squared plus 3x plus 6, and the function gx equals absolute value of 2x. So the situation is going to be more or less like this. Notice that we have the absolute value of 2x, which is the line minus 2x for the negative values, and the line to x for the positive values. And then we have the quadratic function on top of this. Now the area is going to be given by the two enclosed functions, and we're going to have again that the intersection points are going to determine where the integral is going to start and end. So for this scenario, let's actually go ahead and check for that. So we have where is minus x squared plus 3x plus 6 is going to be equals to minus 2x, and that's going to give me the negative intercept. And where minus x squared plus 3x plus 6 is going to give me 2x, and that will give me the positive intercept. So in this case, I can think of it as x squared, move it to this side, minus 5x minus 6 equals 0. And so if we factor this out, is x minus 3 and x minus, well, no, that's not it. Multiplication should give me minus 6 and sum minus 5. So it's actually going to be x minus 6, x plus 1. From these two values, we know that this is x equals 6 and x equal minus 1. So from that information, we know that we're going to get here minus 1 as the intercept, since it gotta be a negative number. From this equation over here, we're going to get x squared and then minus x minus 6 equals 0. And this is multiplication will give me 6 and the sum minus 1. So x minus 3 and x plus 2. That will give me x equals 3 or x is equals minus 2. But since we're in the positive side, we know that it gotta be x equals 3. So that's going to give me my second intersection point, which is 3. And then from that, we can calculate the area enclosed, which is going to be the integral from minus 1 to 3 of the function on top minus the function below. Who's the function on top? Well, in this case, the quadratic is the function on top, but the situation will change. Situation will change on who is in the bottom, depending of the situation. So we gotta solve this absolute value, and we gotta split the integral from minus 1 to 0, in which case we have minus x squared plus 3x plus 6 minus, and then minus 2x, and then plus the integral from 0 to 3 of minus x squared plus 3x plus 6 minus 2x. These two integrals are going to provide the solution for our area. Now, if we look at that in more detail, notice that we're going to have a split in these two areas, R1 and R2, and we can compute those particular integrations as usual by the fundamental calculus theorem. Each of the intervals that this example is using is going to be computed, and we're going to get that the full area is 50 over 3. Now, in terms of analyzing a little bit better the approximation that are taken, you always need to draw a small piece to be able to check what are the functions that are being used. So for example, with this small rectangle here, I can say, well, on the top I'm using the minus x squared plus 3x plus 6, and below I'm going to use the minus 2x line. On this side, it changes, and now I'm using a 2x positives. While on the top, I keep using the same function. So sometimes the area is going to be split in different regions, and it's not going to be as obvious as in this case that we can do it with the absolute value. And many functions can interact or even change who's on the bottom and who's on the top. Now, in some cases, it's going to be convenient to reverse the roles of x and y. So, for example, if we have functions here like this, we have x equals f of y, is going to be more easy to compute the integral in terms of y than to compute in terms of x, since we don't really have a function of x in this case. This other scenario is something where it's much more easier to put the functions in terms of y than in terms of x, or that split the area in a way that we can compute it with functions of x. So just take into account that we might have to reverse the way that we're thinking on our functions. Those cases, though, they don't make any difference with respect to what we use. As you can see, if we're talking in terms of y, then we take a delta y as the base of the rectangle, and we take f of y minus g of y as what is the height of the rectangle, or we can think about it as shifting the height and the width, and just analyzing what the different areas are going to be. At the end, we just make a sum of all this, and if we're just talking about areas with respect to y, essentially it's going to transition to a full integral in terms of y, where the interval is in terms of y as well, and we have f of y and g of y as the dominant functions of our specific case. To do an example of this, consider the following function. We have the region bounded by the graph of y equals x cubed and y equals x plus 6. Notice that if we write that, that is going to give us the need for two regions, because the x cubed function is going to give me this, and the x plus 6 is going to give me this. And not all the time this region is necessarily going to be bounded by the two functions. This small region here is only bounded by the x plus 6 function, and there is no need to include the x cubed. So as you can see, the first part of the area from minus 6 to 0 is just the function x plus 6 minus 0. But second, from 0 to 2, then we can talk about x plus 6 minus x cubed, and that is going to characterize our second area, and it's going to give us a different integral. Now, notice that if you flip around this area and you think about it in terms of y, you're just going to need one integral. The integral of the difference of this function in terms of y minus this function in terms of y. So this is how it will look. I can transform x cubed, y equals x cubed instead in x equals y to the 1 over third. And I can transform y equals x plus 6 instead in the function y minus 6, x equals y minus 6. Now I can check the intersection points, and of course it's going to go from 0 to 8 in terms of y. And now the function on top is going to be the y to the 1 over cube minus y minus 6. Now another example of this situation is going to be find the area of the region in the first quadrant bound by the curves y equals x to the 2/3 and y equals x minus 4. So if you take a look to this in terms of x, it's going to be very difficult to just manage in x, because we have two regions. You got to split here from 0 to 4, which is given by the first function, the function x to the 2/3, and another one where we go from the x to the 2/3 minus the function x minus 4. If we flip everything to y, though, we can think instead this is the function y plus 4 and the function x equals y to the 3 halves. And so now the top function will be the line y plus 4, and the bottom function is going to be y to the 3 halves. So we're just flipping around who's going to be the integration order. Now in y, we had before that in x we had before that we're going from 0 to 8 to cover this whole area. But if we do it in terms of y, we're just going to need to go from 0 to 4. And so that's why the integration here goes from 0 to 4. Now, notice that there is an alternative way to determine the area of that region. And this is something that you can also do by common sense. And is this area is producing a triangle, right? So we can compute the area of that triangle, which is given here by the region R2. And so what we can do is calculate the area of R by doing the full area of R1, which is only the area covered by x to the 2/3 from 0 to 8, and then subtract the area given by the line x minus 4, or that triangle, and just subtract the two areas. So now on part 2, I'm going to go over some more examples of this and how to go over the following exercises bit by bit, making all the areas and expressing the integral. So see you in part 2.